Good morning, Dr. Meran. I'm Chong Bin Yong, and today our team will present our network analysis project for NET 2201. We will walk you through our methodology, findings, and key insights from real-world network traffic analysis. In this assignment, we have analyzed three key areas: TLS 1.3 encrypted communications, modern QUIC protocol, and traditional DNS TCP UDP. Our goal was gaining practical protocol analysis experience and real-world troubleshooting skills. For methodology, we have used Wireshark for 10-minute live traffic capture, analyzed application layer protocols, examined TCP UDP behavior, and simulated DNS misconfiguration for troubleshooting practice. Now, let's examine our analysis of three critical application layer protocols from our live traffic capture. Starting with DNS. We capture a query for beacons.gcp.jvt2.com in packets 49 and 59. The matching transaction ID OX3AFE confirmed this request response pair completed in 5 milliseconds. Notably, the server returned 0 answer records, demonstrating that DNS provide proper responses even when requested records don't exist. This is normal and a healthy DNS behavior. For TLS 1.3, we analyzed the handshake to tunnel.googlezip.net in packets 438 and 440. The client offers 16 cipher suites, and the server selected TLS AES 128 GCM SHA-256, completing the entire handshake in just 18.8 milliseconds. This showcases the significant efficiency improvements TLS 1.3 provides over earlier versions. Finally, QUIC represents next-generation protocol design. In packet 63, we observe a QUIC initial packet containing 3 frame types: ping for connectivity testing, padding for packet size requirements, and crypto containing encrypted TLS 1.3 handshake data. This demonstrates how QUIC merges transport and security layers, operating over UDP port 443 to achieve lower latency than traditional TCP plus TLS approaches.
So now I would like to talk about TCP and UDP deep dive. First, I would like to talk about three-way handshake, where in our simulated network we found that packet 435, 436, and 437 is one of the three-way handshake that has occurred. So usually in the first handshake, it usually means the initial SYN where it track data using sequence and acknowledgement number. And for the second handshake, in the packet we can see the SYN and ACK, which indicates the server reply. And ACK equals to 1 is the acknowledgement of the client SYN. And for the third handshake, usually in the packet it will show the sequence equals to 1 and ACK equals to 1. Where ACK equals to 1 means the client successfully received the server initial SYN. It means that it has successfully exchanged and acknowledged each other's synchronization messages. As we move on, the second will be the termination sequences, which also means a four-way handshake, that we found out that packet 458, 460, 461, and 462 is the termination sequences that has occurred. So the first handshake usually means the client has sent an initial connection termination, and the second is the server response from the server to the client FIN. The acknowledgement number will also increases by 1 as well, and for the third handshake, it usually is the server sends its own FIN and ACK to signal done setting data. And for the fourth handshake is the client acknowledges the server FIN, and the final ACK will complete the connection termination. As we move on, it will be the TCP retransmission. So packet 130 is one of the TCP retransmission where it presents a resend of an earlier SYN packet, an initial attempt to initiate a TCP connection between client and server. And based on this, we can say that because of the color scheme rule in Wireshark indicates the TCP retransmission. So we also find some evidence to support the claim. So the first evidence will be the packet detail pane, where it says that RTO based on data from frame 100 means that frame 1 also equals to packet 100. And then second will be the identical content include fields from both the IP and TCP header. So this one could be linked to evidence 2, as you can see the TCP header discussion where packet 100 and packet 130 has the identical IP and TCP header. And for the evidence 3, which is a timestamp comparison, because RTO means the retransmission timeout. So for retransmission timeout has a 1 second delay rule. So we can compare the differences in time between packet 130 and packet 100. The results show that the differences in time is actually 1 second. So this actually apply to the RTO rule. So which means that packet 130 is a retransmission of packet 100. So now as we move on to compare and contrast TCP and UDP in terms of reliability, delay, and protocol complexity. For reliability, TCP provides reliable delivery through sequence number, acknowledgements, and RTO, and also ensure in order and complete data transfer, but it has higher overhead due to connection management. In UTP, it is suitable for applications where occasional loss is acceptable, let's say video, but it is unreliable because no guarantee of delivery or order, no in transmission or acknowledgement mechanism. And for delay, TCP has a more reliable because of the latency before data can flow, and it has a three-way handshake mechanism. And TCP must be acknowledged before the data can be sent, but it takes the time for the data to be processed from the client to the server side. And UDP is lower latency and without prior setup, but risk of loss or reordering due to no confirmation. And the last but not least is the protocol complexity. TCP has a more complex header due to more fields and configurable options compared to UTP. The more fields includes flag, sequence, add numbers, window size, and options like MSS, SEC, and WS. But it's more resource intensive due to extensive header. In regards to UTP, only has 4 fields in the header, which is the source port, destination port, length, and checksum. UTP's simplicity enables faster throughput, but no built-in flow control or connection handling.
First, we start with unicast. This is a one-to-one transmission where data is sent from a specific source to a specific destination. In our capture, we saw a packet going from one IPv6 address to another with distinct MAC addresses. Unicast is a common in web browsing, emails, and file transfer. It is efficient for targeted delivery but can waste bandwidth if the same data is sent repeatedly to many users. Second, we have broadcast communication. Here, a packet is sent to all devices on the local network. In Wireshark, this is easy to spot with a destination of MAC of WF. It is used in protocol like ARP and DHCP. While useful, it can cause network congestion and raise security risks, since all devices receive the data. Third, we have multicast. Multicast is like a middle ground. It sends data from one source to multiple specific recipients who are part of a group. It is more efficient than broadcast and is often used for streaming, software updates, or online gaming. But if access control isn't set properly, it can be exploited. Fourth, we have IP fragmentation. IP fragmentation happens when a packet is too large for the network maximum transmission unit. So it's broken into smaller pieces, like in our packet 39 and 40. While it allows large data to pass through small links, it adds delay, and if even one fragment is lost, the entire datagram has to be resent. For the fifth one, we observe packet loss in packets 484 Wireshark flag missing TCP segments, showing that TCP previous segment not captured. This can be caused by network congestion or errors and forces the sender to retransmit, delaying communications. Finally, we have time to live expiration. Time to live is a field that limits how many routers a packet can cross. In our example, TTL was 1 and ICMP is type 11 and the code is 0. TTL is exit, so it expired immediately and trigger an ICMP error. This protects the network from infinite routing loops and help in tools like traceroute. That's an overview of our packet level insight. Thank you.
The network issue chosen demonstrate how a simple DNS server misconfiguration can completely disrupt internet connectivity. For this demonstration, we intentionally created a DNS misconfiguration by setting the primary DNS server to an invalid address, such as 5.6.7.8. Next, we disable the IPv6 protocol support and leave the alternate DNS server field blank. This configuration eliminates all DNS resolution capabilities, which prevent the system from translating domain names like www.google.com into their corresponding IP addresses. As expected, this results in complete failure of web browsing and any applications dependent on domain name resolution. Our initial testing using command line tools to confirm the issues by the command nslookup www.google.com, which show us repeated DNS request timeout messages, and ping www.google.com, giving us result of field with could not find host errors. These results clearly indicate that our DNS server configuration was invalid and non-responsive. Moving on with Wireshark packet analysis, we first using Wireshark to filter out the necessary packets we capture for analyzing the network traffic, reviewing three important categories of DNS-related packets. The first category, standard DNS AIR record queries, which also known as IPv4. From the analysis, all these queries from our client to the invalid DNS server 5.6.7.8 that we configured before, they are requesting IPv4 address for www.google.com. And the key finding of this analysis is there are a clear retransmission pattern starting with the packet 182 followed by exponential backoff intervals of 1, 2, and 4 seconds, which we gotten from our command line tools before.
This screenshot shows DNS queries made to resolve the IPv6 address of www.google.com. These are AAA record queries which are used to get IPv6 addresses. What's interesting here is that even though IPv6 was believed to be disabled on the systems, this query was still sent. This tells us that either IPv6 wasn't completely turned off or some applications are explicitly trying to use IPv6 anyway. These packets were sent to the DNS server 5.6.7.8, which is actually an invalid DNS server, resulting in no replies. Wireshark flagged this with the warning DNS response missing. This contributes to DNS resolution failure. Here's the breakdown of the IPv6 DNS packet header. The source IP address is 192.168.68.53 and is sending to 5.6.7.8 over UDP port 53, the standard DNS port. The query type is AAA, which means it's the specifically requesting an IPv6 address. As you can see, there are no answer or authority records in the packet, confirming that the query were unanswered. Again, we get the DNS response missing warning from Wireshark. The next type of traffic is multicast DNS or MDNS, which is commonly used for local device discovery. In this case, a different device with IP 192.168.68.51 is broadcasting queries looking for Google Cast services. These queries are sent to the multicast address 222.0.0.251, which is reserved for MDNS. This is unrelated to the IPv6 misconfiguration and is the normal part of local network discovery, especially for smart devices like Chromecast. Again, we see the DNS response missing warning, but this is expected if no Google Cast devices are currently available to respond. This shows the header details of the MDNS packet. The source and destination port are both 5353, which standard for MDNS. The query is a PTR record, which is used to find services like googlecast.tcp.local. Just like the previous slide, There are no answers returned. Again, this is common unless there's an active device broadcasting a matching service. This is our presentation. Thank you for your time and attention.